Bags of Chips Ahoy chocolate chip cookies claim that they have 1,000 chips in every bag. Do they really have 1,000 chips in every bag? A group of Air Force cadets bought bags of Chips Ahoy cookies from all over the country to verify this claim. They hand counted the number of chips in 42 bags. They wanted to know, is the mean number of chips per bag greater than 1,000? To answer this question, we can do a hypothesis test. The first step of our hypothesis test is to state the hypotheses and define the parameters. We're going to define mu as the mean number of chips per bag. In that case, our hypotheses are going to be null hypothesis mu equals 1,000 and alternative hypothesis mu greater than 1,000. Next, we're going to check our conditions. The conditions for doing the one sample t procedures are that either our sample size is large, 30 or more, or that our population is normally distributed. In this situation, our sample size was 42, which is larger than 30, so we do meet the conditions for this test. Next, we're going to calculate the statistic from our sample. In this case, we have x bar. X bar is equal to 1,261.6 based on their data. Next up, we'll calculate the standard error, which will later help us to find the test statistic. The standard error when we're dealing with one mean is equal to s over the square root of n. In this case, our s value was 117.6 and our sample size was 42. So our standard error is going to be 117.6 divided by square root of 42, which equals 18.146. Now we're ready to find the test statistic. The test statistic for a single mean is a t statistic, and it's equal to x bar minus mu naught divided by s over the square root of n. Now, when we talked about proportions, we were dealing with normal distributions. But when we're dealing with means, we have to estimate more things from our sample. We're estimating both the standard deviation and the mean. Estimating more things introduces a little bit more variation into our final result. So our resulting value is no longer distributed as a normal distribution, but is instead distributed with a t distribution. T distributions are pretty much just like normal distributions. They're single peak, symmetric, they're bell-shaped. The basic difference between a t distribution and a normal distribution is that a t distribution is a little bit flatter and a little bit more spread out. We can identify a particular t distribution by identifying the number of degrees of freedom. For a test of a single mean, then degrees of freedom are equal to n minus 1. So here's our formula for the test statistic. We take the 1,261.6 minus mu naught, and mu naught is just the value that we're claiming mu is under the null hypothesis. So in this case, that's 1,000. And we divide that by s over the square root of n. Now we already computed that quantity, that standard error quantity, so we can just plug that right in here to the denominator of our test statistic formula. And we get 14.4. So 14.4 is our test statistic. And we use the test statistic to help us find the p-value. Now, in order to find the p-value, we're going to need to know how many degrees of freedom that we have. So in this case, we had a sample size of 42, and degrees of freedom are equal to n minus 1. So 41 minus 2 equals 41 degrees of freedom. And we have an upper tail test. We know that because we had a greater than in the alternative hypothesis. And we can usually tell just by looking at the value of the test statistic, which in this case is positive. All right, so now I'm going to go over to StatKey and we'll see how we can find the area in the upper tail that is greater than 14.4, which corresponds to our p-value. Here in StatKey, I come down here to where it says theoretical distributions, and I'm going to choose t because I'm dealing with the t distributions. When I click on that, it's going to ask me for the number of degrees of freedom, which I've already found to be 41. So I hit 41, click on OK, and I'm doing an upper tail or a right tail test. Again, because my alternative hypothesis said greater than, I know it's right tail. So now I just need to enter in the value of my test statistic. Down here at the bottom, I put in the value of 14.4 as my test statistic and click on OK. Once I do that, the value in this little floating box is going to be my p-value. And as you can see by my picture here, looking at the area, my test statistic was huge. And a big test statistic means we're going to have a small p-value. And my p-value is really small. It's essentially 0. All right, so back here, my p-value is essentially 0. And we know that when p is low, HO must go. So when I draw my conclusions, I would reject the null hypothesis because this provides extremely strong evidence that the average number of chips per bag of Chips Ahoy cookies is greater than 1,000. Now, on the exam, of course, you're not going to have stat key in order to find the p-values. Instead, you're going to use tables. So let's see how we would find the p-value for this problem using Table A. So here's an excerpt of Table A. I've kind of deleted the middle so I could make the whole chart a little bit bigger. When we're looking for p-value, what we need to do is we need to find the row for the number of degrees of freedom that we have. So looking down this side over here, the left side is where it has the degrees of freedom. I'd be looking for 41. Notice that on my table, I only have the option of 40 or 45. When we're looking at degrees of freedom, we always round down. So in this case, I would round down to 40 degrees of freedom. Now I'm going to look along the row for 40 degrees of freedom, and I'm going to look for where the absolute value of my test statistic would fall. So if you recall, my test statistic was 14.4. So I'd try and look here to see between what two numbers would 14.4 fall. And as you see pretty quickly, the largest number here is 3.55. That means 14.4 would be way, way over here to the right. And if you look at the values up here where it says one tail area, you can see that they are getting smaller and smaller as we move from left to right. So if I was to keep moving over to the right, my one tail area value would get even smaller. That means that my p-value then would be less than the smallest thing that they have on the table. So in this case, less than 0.0005 since I had a one-tailed test. How did I know I had a one-tailed test? Back to the alternative hypothesis where we had a greater than. If it's greater than or less than, it's a one-tailed test. And if it's not equals to, it's a two-tailed test. So here in Table A, we would just choose the appropriate row to match up with our alternative hypothesis. One tail for a one-sided test and two tail for a two-sided test. All right, so now I know that there are more than 1,000 chips in every bag on average. But how much more? What is the average number of chips in each bag? We could do a confidence interval to answer this question. We're going to go ahead and do a 99% confidence interval. The formula for a confidence interval for one mean is x bar plus and minus t star times s over the square root of n. And again, the degrees of freedom for our t star is going to be n minus 1. So first thing we do is define that parameter. It's the same as before. Mu is equal to the mean number of chips per bag. Then we're going to check the conditions. The conditions when we're dealing with means are the same regardless of whether you're doing a hypothesis test or a confidence interval. So our conditions were that either the sample size was large, in other words 30 or more, or that our population was normally distributed. In this case, our sample size is larger than 30, so we automatically meet the conditions for this test. Next, I need to find my t star to use in my confidence interval formula. To find t star, again, I'm going to have to know the number of degrees of freedom, which we've already found to be 41. Now, I can use stat key to help me find my t star. So I'm going to go back here into stat key. In stat key, again, I'm going to choose the theoretical distribution for the t distribution and enter in 41 as my degrees of freedom. Now, I wanted to do a 99% confidence interval. To find t star, I click on the two tail area, and then in the center box, I put my level of confidence. So I want it to be 99% confident, so I put 0.99 in the middle there. Once I do that, the value down here in the right box on the bottom is going to be my t star value. So I'm going to use a t star of 2.701. All right, now I'm ready to compute my confidence interval. So I take my sample mean plus and minus the t star that I just found times the standard error, which is s divided by square root of n. Plugging in all those numbers, I get 1,261.6 plus and minus 2.701 times 117.6 divided by square root of 42, which ends up giving me a margin of error of 49.01. Now I just add and subtract that margin of error from my sample mean, and that gives me a confidence interval that goes from 1,212.59 to 1,310.61. Finally, I write a sentence interpreting my confidence interval. I'd say, we are 99% confident that the mean number of chips per bag is between 1,212.59 and 1,310.61. Now again, on the exam, you're not going to have stat key to help you find T star values. So let's look at how we would find T star using Table A. So here's what Table A looks like. To find a T star value, we're going to look for the row for the number of degrees of freedom that we have, and we're going to see where that corresponds with the middle area for the level of confidence that we want to have. In this case, as we look at the degrees of freedom, again, we realize that there is no row for 41 degrees of freedom, so we're going to have to round down and use the row for 40 degrees of freedom. We want to be 99% confident, so I look for where it says middle area, and I find the one for 0.99, which is right here. Looking at those, the row for 40 degrees of freedom and the column for 99% confident, the place where they intersect is going to be the value of my T star. So in this case, that is 2.704. So you notice that it's very, very close to what we got using stat key, but the one on stat key is going to be a little bit more exact because it can handle any number of degrees of freedom, whereas our table only has some values for degrees of freedom.